Well, we're ready for our third presentation this afternoon. It's by Nevin Daniel, who's from Ward Melville High School in East Setauket, New York. And the title of his talk, and he's going to repeat it, I know, is Novel Asymmetrical Bowtie PAMAM Dendrimer Conjugates as Model Systems for Anticancer Taxoid Drug Delivery. So, Nevin, come on up.
Good afternoon, everyone. My name is Nevin Daniel, and today I'll be presenting my work on novel anticancer dendritic drug delivery conjugates. So cancer is any one of more than 100 afflictions that arise from uncontrolled cellular proliferation that results from oncogenic mutations. More than 1 million people are diagnosed with cancer every year. However, while most of these people are men over age 55, all people are susceptible to cancer. Furthermore, in the United States alone, 1 in 2 men and 1 in 3 women can expect to have some variant of cancer in their lifetime. As the chart shows, cancer is currently the second leading cause of death in America. However, as of 2005, cancer surpassed heart disease, the first leading cause of death, as a leading cause of death among Americans under the age of 85. Furthermore, despite extensive research, death rates in cancer have only fallen by about 5% since 1950, compared to heart disease, which concurrently has its death rates fallen by about 30%. Thus, scientists have generally agreed that an ideal future cure for cancer would be one that is chemotherapeutic, due to its potential to be both non-intrusive, specific, as well as logistically simple. However, current chemotherapeutic regimens have many problems, which can be honed into 4 major ones. 1, they do not actively target cancer cells with a tumor targeting module. 2, they do not passively target cancer cells by having a high plasma circulation time, which allows for the enhanced permeability and retention effect to take its full effect. 3, they do not have a calculated drug payload and are just administered incalculably into the body. And 4, they do not release cancer drugs in a controlled manner. Thus, the aim of my project was to alleviate these 4 major concerns with current chemotherapeutic regimens. And in my project, the effective drug that I used was a Taxoid derivative called SBT1214. Paclitaxel is a widely used cancer drug today for aggressive cancers. It is a mitotic inhibitor that hyperstabilizes tubulin in the mitotic spindle. And this, through caspase cell signaling activity, causes apoptosis. However, paclitaxel itself faces many problems, including low yield from the bark of the Pacific yew tree from which it is taken, low efficacy, as well as various side effects. Thus, scientists have recently made 2nd and 3rd generation taxoids, such as SBT1214, that show higher efficacy. As shown in the chart, SBT1214 has shown more than 2 orders of magnitude greater efficacy in breast, lung, and ovarian cancer cells than paclitaxel. Also in my drug delivery system, I use the vitamin as a tumor targeting module. Russell Jones et al. Has shown that since cancer cells need to sustain rapid cellular proliferation, they often overexpress certain vitamin receptors, namely biotin, folic acid, and vitamin B12. Thus, these moieties can act as effective tumor targeting modules that enter the cell via receptor-mediated endocytosis. Here's a diagram of that same process. Basically what happens is a vitamin binds to an exterior protein on the cell membrane, and thus this encourages a vesicle to be formed that encloses the entire drug delivery conjugate. Initially, this vesicle is coated by clathrin. However, this depolymerizes and then merges with the lysosome, where the drug is released from the drug delivery system it is held in. Now, the basis for my drug delivery system was the polyamidoamine dendrimer. Dendrimers discovered by Tamali et al. In the 1980s are basically roughly spherical nanoparticles that consist of a repeating amount of amidoamine branches. They consist of 3 major parts: an initiator core, the branches, as well as the terminal amine groups. Scientists have currently engineered both the core and the branches. The core that I used was a cysteamine core, and the branches have been modulated such that they can be of various generation or divisions in the amidoamine branches. And this varies the size of the dendrimers from anywhere from 2 to 10 nanometers. So dendrimers have 4 main advantages in drug delivery. 1, they're biocompatible. 2, they sufficiently increase the molecular weight of the drug delivery conjugate such that the EPR effect takes effect. Also, they have a large and quantitative number of functional handles for moiety conjugation. And finally, they are easily engineered and also commercially available. So the objectives of this research was to design a dendritic drug delivery system that alleviates many of the aforementioned concerns with current chemotherapy. I also want to develop the synthesis pathways to 2 such examples of this system. One was a fluorescent probe conjugate that would be used in internalization studies, and a drug conjugate to be used in further cytotoxicity assays. I then wanted to synthesize these conjugates and characterize them with NMR multi-top spectroscopy. The conjugate design was as follows. Generally, a generation 3 half dendron was conjugated with a 1,8 bis malamido octane core to a generation 1 half dendron. The generation 3 half dendron was conjugated to a drug linker conjugate in the drug conjugate, as well as fluorescein isothiocyanate in the fluorescent probe. The generation 1 half dendron was functionalized with biotin OSU as a tumor targeting agent. Synthesis began with the functionalization of the generation 1 half dendron. Biotin was first used or coupled with N-hydroxycinamide through DIC coupling, and then it was coupled to the generation 1 PAMAM dendrimer. This was subsequently cleaved by nucleophilic attack by TSEP. Synthesis then continued with the creation of a second generation disulfide linker. The linker operates basically on selective release by glutathione, which is an in vivo reducing agent. Due to high concentrations of oxygen inside the blood, glutathione is found in 1,000 times less concentration in cancer cells than in the blood. And thus, since the linker operates on selective release by glutathione, it selectively releases drug within cancer cells. Additionally, in my linker, I enhanced previous versions by adding a methylene group in between the aromatic fragment and the aliphatic linear chain. This led to less polarization of the disulfide bond and thus enhanced cleavage half-life. Synthesis of my drug delivery system continued with the creation of the linker, as mentioned. First, ethyl 4-bromobutyrate underwent a nucleophilic substitution with thiourea. The resulting thiuronium salt was hydrolyzed with sodium hydroxide to form 4-mercaptobutanoic acid. This then was TIPS protected for further use. The aromatic fragment of my linker began with a ring opening of 3-isochrominone. This then underwent a similar nucleophilic substitution with thiourea and then cleavage with sodium hydroxide. This was then reacted with dipyridine disulfide in a thiol disulfide exchange, and then was coupled through DIC coupling again with SBT1214, the potent Taxoid. This was then attached to the aliphatic linear chain through another thiol disulfide exchange, and then was deprotected when coupled, as well as coupled to N-hydroxycinamide to be coupled to the dendrimer. Synthesis continued with the creation of the malamide core used to connect the two half dendrons. Firstly, 1,8-diamino octane was coupled with maleic anhydride through intramolecular coupling, and then intramolecular cyclization formed the final 1,8 bis malamido octane. The fourth phase of synthesis consisted of the making of the fluorescent probe. Generally, what happened was FITC, or fluorescein isothiocyanate, functionalized the generation 3 PAMAM dendrimer. This was then cleaved nucleophilically with TSEP, and finally attached to the malamide core. This was then recoupled to the tumor targeting generation 1 half dendron to form the final fluorescent probe conjugate. Synthesis concluded with the creation of the SBT1214 drug conjugate. Firstly, the dendrimer was cleaved by TSEP and then attached to the malamide core. It was then coupled to the SBT1214 linker construct, and finally recoupled to the tumor targeting generation 1 half dendron to form the final SBT1214 drug conjugate. The conclusions of this study then were the successful design and synthesis design of a novel dendritic drug delivery system that alleviates many of the major concerns with current chemotherapeutic regimens. Additionally, we successfully designed the synthesis of a novel second-generation disulfide linker. In the process of these two syntheses, we have created many novel dendrimer and linker reactions which could certainly revolutionize the fields of disulfide linker technology as well as dendritic drug delivery. Future work entails the use of the SBT1214 conjugate and fluorescent probe for their various purposes. First, I'd like to study the internalization by dendritic drug delivery system using fluorescence-assisted cell sorting analysis, as well as confocal microscopy. I'd also like to study the cytotoxicity of my system within cancer cells using MTT assays and other such assays. Thirdly, I would like to study the linker stability of my theoretically enhanced linker to establish proof of concept through STS page analysis. And finally, apply my system as a model system for chemotherapeutic drug delivery of the future by modulating the various aspects, including the tumor targeting module, the drug, as well as the linker, in order to see if it can be used effectively in the mass market. I would like to acknowledge the following people for their support in my work, including my mentor, Dr. Iwao Ojima, as well as my supervisor, Mr. William Berger, as well as Siemens, College Board, and George Washington University for providing me with this invaluable opportunity.